Fish populations have rather interesting behaviors. Sometimes the fish populations grow very quickly and they boom, and then the next year they bust. This is called a boom-bust cycle in fish. And it's very common in Pacific salmon. When your Pacific salmon runs are very high, and then the next year they can be very low. So there are a couple of different models I want to look at today, and they're all put together by fisheries biologists. The first is called the Beverton-Holt model, and it models the population size at time t plus 1 as a function of the population size at time t, and this is a function right here. When we graph this function, it's shown by this curve right here, given by function f1. Another model is called the Ricker model, and its xt plus 1 is f2 of xt, and this is a function right here for the Ricker model. And when we graph the Ricker model, it grows, it has a maximum, and it comes back down. In fact, if you look at this model, it's very much like the blood alcohol model that we saw in a previous video in terms of a function that grows, peaks, and comes back down, which is kind of interesting. So if we want to understand the difference between these models, then we can look at the stability of the equilibria. You can see graphically that each model has a zero equilibrium, where the function crosses the 45-degree line, and each model has a positive equilibrium. The one for Beverton-Holt is shown right here, and the one for the Ricker curve is shown right here. So let's think about the stability of these equilibria and see if we can use our understanding of the stability to understand the fish population itself. So the first thing we want to do is actually calculate the values for the equilibrium. And so we'll start with the first one, and that's for Beverton-Holt. And so an equilibrium satisfies the following equation. X hat is 9x hat over 1 plus 8x hat. We can cross multiply to get x hat into 1 plus 8x hat is equal to 9x hat. And then we can write this out to get x hat plus 8x hat squared minus 9x hat is equal to 0. And so if we simplify this, we can write it as 8x hat into x hat minus 1 is equal to 0. And so that says either x hat is equal to 1 or x hat is equal to 0. And so here we have x hat is equal to 1 for the Beverton-Holt curve, and we have the 0 equilibrium as well. Okay, let's work it out for the Ricker curve, and we do something kind of similar here. We write x hat is equal to 9x hat e to the minus 3 x hat. And so if we bring everything over to the left-hand side, we're going to have x hat minus 9x hat e to the minus 3x hat is equal to 0. You can pull out a common factor, which is x hat. We have x hat into 1 minus 9e to the minus 3x hat is equal to 0. And so either x hat is equal to 0 or 9e to the minus 3x hat is equal to 1. So let's focus on this second possibility here. And so that's going to give us that e to the minus 3 x hat is equal to 1 over 9. And because we have an exponential, we want to undo the exponential so as to calculate the value for x hat. We take the log of both sides. And so we have minus 3x hat when we take the log of the left-hand side. And when we take the log of the right-hand side, we have the log of 1 over 9, which is equal to the log of 1 minus the log of 9. The log of 1 is equal to 0. And so we get x hat is equal to the log of 9 over 3. Or our original one was x hat is equal to 0. And the log of 9 over 3 is approximately equal to 0.73. So this is we have x hat is approximately 0.73. Notice we have both of the dynamics on the same axes because we want to kind of compare and contrast them. Okay, so this is the first step, calculating the equilibria. The second step would be to take the derivative of each of the two functions here and then use these to calculate the stability using the stability conditions. So to start with, I'm just going to write down the derivatives for f1 and for f2, and I suggest that you might want to check these. I'll just write them down here. So derivatives. So for the Beverton-Holt, we want f1 prime of x, and that equals 9 over 1 plus 8x all squared. And for the Ricker model, we have f2 prime of x, and that's equal to 9e to the minus 3x into 1 minus 3x. Okay, so we're going to use these when we calculate the stability condition. Notice that for the Beverton-Holt model, this is always greater than 0. And so as we see in the picture here, the f1 function is an increasing function. For f2 prime, it'll be less than 0 if x is bigger than a third, and greater than 0 if x is less than a third. And the maximum comes right at the point where x is equal to a third. And so this point right here is 1/3. Okay. The next step will be to take the values of each of the equilibria and put them into the appropriate derivative to calculate the stability condition. Okay, let's go ahead and evaluate the stability conditions. So the stability condition is as follows. If the absolute value of f prime of x hat is less than 1, it's stable. And if the absolute value of f prime of x hat is greater than 1, it's unstable, where here x hat is the equilibrium point. So let's consider model 1 here, which is our Beverton-Holt model. And we have x hat is equal to 0 or 1. F prime of 0 is equal to 9 over 1 plus 0 squared, which is equal to 9. And so we have the absolute value, f prime of 0 is equal to 9. So it's unstable. If we look at f prime of 1, we have that's equal to 9 over 1 plus 8 times 1 all squared, which is equal to 1/9. And so the absolute value of f prime of 1 is equal to 1/9. And so that's stable. Okay, so we can label the equilibria on the diagram here as being unstable and stable. Let's look at the second function. This is the Ricker function that has this interesting shape where it goes up and comes down. And we have our two values for x hat. X hat is equal to 0 and log 9 over 3. So let's look at 0 first. F prime of 0 is equal to 9 e to the 0 times 1 minus 0 is equal to 9. So then we have f prime of 0, absolute value is equal to 9. And so it's unstable. Let's look at the second equilibrium. And we have, I guess we need to put a 1 on these guys here, just to be clear about it, and a 2 on these guys, because it's the second function. So f2 prime of log 9 over 3 is equal to 9 e to the minus log 9, e to the minus 3 times log 9 over 3 times 1 minus 3 log 9 over 3. Okay, so we see that the 3's are going to cancel in two places. And so we can write this as being 9 e to the minus log 9 into 1 minus log 9. And we have a negative power here in the exponential. So it's quite handy to write this as being 9 over e to the log 9 into 1 minus log 9. Now this is just a very fancy way of writing 9 on the bottom here, because the exponential function and the natural log function are their inverses of each other. And so this is just equal to 1 minus log 9. And this is equal to approximately minus 1.19. And so in this case here, when we take the absolute value of the derivative of f2 evaluated at log 9 over 3, this is equal to 1.19, and this is bigger than 1, and so the equilibrium is unstable. Okay, so if we mark it on the graph here, we see that we have an unstable equilibrium at 0, and we also have an unstable equilibrium at the x is equal to the log 9 over 3, which is approximately equal to 0.73. So these are two different kinds of graphs qualitatively. One has an unstable equilibrium and a stable equilibrium, and the other one has two unstable equilibria, which is kind of cool. So let's see if we can understand what's going on here by cobwebbing. If we start with some initial value for our population with the Beverton-Holt curve, and then we go up and we calculate our x1, x2, and so on. We're moving towards the equilibrium point, and that's what our calculation told us. It was stable. And we end off moving towards x hat is equal to 1. This is a slightly different circumstance here. Suppose we start with some value x naught that's maybe fairly close to the equilibrium point, and then we calculate x1. We're going to be above the equilibrium point, and then we're going to come down, we're going to go over, we're going to jump up, and you can see that this population is going up and down at each successive time step. And so this is the boom-bust kind of dynamics that we often see with fish populations. And this situation with the Beverton-Holt curve is often called compensation or compensatory dynamics. And then this one with the Ricker curve is often called overcompensation. Overcompensation, because when the population gets high in one time step, it overcompensates and it crashes the next time before becoming large the next step. And so a lot of fisheries biologists are very interested in these overcompensatory dynamics because they really can describe what's going on with a lot of salmon, such as the Pacific salmon, where people are concerned about their long-term viability, but we're seeing the populations go up and down between very large populations and very small populations over time.